Okay, this is the fourth and last proof that we're going to do for this lesson. We're trying to prove things about the angle relationships when parallel lines are cut by a transversal. And this is the fourth idea, the fourth theorem. It's the consecutive interior angles theorem. So this theorem says if two parallel lines are cut by a transversal, then the pairs of consecutive interior angles are supplementary. So this is the only one of the four theorems that we talked about today where the conclusion is that they're supplementary and not congruent. So be careful there because this is kind of the odd man out. The other thing is that this is actually the converse of Euclid's fifth postulate. So in the first video we talked about how Euclid, he starts with this postulate and he kind of goes in the opposite direction of us. He proves all the converses of all the theorems kind of in the opposite direction. We started with the corresponding angles theorem, which some people consider to be a postulate as well. And we're working our way the opposite direction of Euclid. And we are going to use that corresponding angles postulate in this proof as well. So that theorem helps us with the alternate interior angles theorem, and the alternate exterior angles theorem, and the consecutive interior angles theorem. So once we have the corresponding angles theorem, that's the important one, and all the other three kind of fall in a row like dominoes. So here's the setup that we're going to use. We're going to have parallel lines cut with a transversal, and we know L is parallel to M. We're going to show that 2 and 3 are supplementary. So 2 and 3 are the consecutive interior. Remember, consecutive means next to each other, and interior means in between the two lines. So alternate interior would be on opposite sides of the lines and next to different lines. So those would be alternate interior, or these would be alternate interior. These are consecutive interior because they're next to each other. Okay, so let's get started. We got L parallel to M given. Oh, and by the way, I'm hoping that your knowledge of how to do proofs or your intuition about doing proofs is growing. I'm hoping that you're getting better at these with experience. So again, just like I said in the last video, what I would recommend that you do for your own learning is to stop the video here and see if you can prove this yourself. See if you can go through and figure out how to do this. Because you have all the tools and all the definitions and all the postulates and theorems that you need. They're floating around in your brain somewhere. See if you can organize them into a valid proof. Once you do that, you can come back to the video and see how I did it and see if they match, see if they make sense. Okay? So go ahead and pause now and finish this if you can. And if you get stuck, come back and watch. Okay, we're back from pausing because you just did this one. Let's see how you did. Okay? So again, our goal is to prove that these are supplementary. Well, we got to start here. We got to start somewhere. We got to start with our given. What does this give us? L parallel to M. Well, that gives us a lot of things now. It gives us, we know for sure all the corresponding angles are congruent. We know all the alternate interior angles are congruent. And we know the alternate exterior angles are congruent. In this particular setup, the only ones that are labeled are these corresponding angles. So what we're going to say is angle 1 is congruent to angle 3. And we can say that because of the corresponding angles theorem. Which, some people consider a postulate, and the reasoning behind it is usually has to do with transformations or specifically translations, like we talked about in the first video. Okay, we're going to have to do a little bit of addition here and some substitution. So what we're going to do is we're going to switch to angle measurement. So we're going to say measure of angle 1 is equal to measure of angle 3. Definition of congruent angles. Okay. The reason why we're going to do this is because when we talk about supplementary, we kind of need to use the idea that they add to 180. And so when we're working with addition, we're going to have to use equality instead of congruence. So the other thing that we know here is we have this linear pair idea, right? So the measure of angle 1 plus the measure of angle 2 has to equal 180 because they form a linear pair. Okay, that's a linear pair postulate. Or you could also use the definition of linear pair. those ideas are pretty similar. When we defined linear pair, we said, you know, they form supplementary angles and they're adjacent, and then of course if they're supplementary, they also have to add up to 180. So anyway, we got this. Now what we can do, because we want to show that 2 and 3 are supplementary, right? And we have 1 and 2. What we can do is we can substitute angle 3 for angle 1. So we can say now the measure of angle 3 plus the measure of angle 2 equals 180. Right? That's the substitution property of equality. We just took this statement and we, instead of 1, we wrote 3. We can do that because these are equal to each other. Okay. So if these two add to 180 and these two are congruent, then these two must add to 180. That's the idea. And they do. And so then we can say, because their measures sum to 180, we can say angle 2 and angle 3 are supplementary. And that's just the definition of supplementary. And we're done. So, linear pair, congruent, therefore those must be supplementary. So not too long of a proof. But again, the point that's really important to make is that when we have the corresponding angles theorem, then we get the other 3. Those kind of follow from that theorem. So that's all 4. Now you got them. These are going to be the four of the proofs that are in your homework today, so that should help you. There's going to be a couple other problems after that where you're going to use these theorems again. But there you go.